The F-35 Lightning II, a fifth-generation fighter, stealthy, supersonic, and incredibly versatile. This aircraft is a marvel of modern engineering. Designed for air superiority, the F-35 boasts advanced stealth capabilities. It evades radar detection, making it a formidable force in the sky. The F-35 is also equipped with cutting-edge avionics. These systems provide pilots with unparalleled situational awareness. Beyond its stealth and technology, the F-35 is a true multi-role aircraft. It excels in air-to-air combat, ground attack, and electronic warfare. This versatility makes it a valuable asset to any air force. The F-35's development represents a significant leap in military aviation. Its advanced capabilities continue to shape the landscape of modern warfare. Designing an aircraft as complex as the F-35 presents immense challenges. Engineers must ensure optimal aerodynamic performance. This is where computational fluid dynamics, or CFD, comes in. CFD is a powerful tool that simulates fluid flow. In the context of aviation, it helps analyze how air interacts with an aircraft. CFD simulations provide invaluable insights into an aircraft's aerodynamics. They reveal how air flows over the wings, fuselage, and other surfaces. By understanding these airflow patterns, engineers can optimize the aircraft's design. They can reduce drag, improve lift, and enhance maneuverability. CFD plays a crucial role in the design and development of modern aircraft. It allows engineers to test and refine designs virtually, saving time and resources. Before a CFD simulation can begin, engineers create a digital representation of the aircraft. This is done using computer-aided design, or CAD, software. The CAD model captures the aircraft's intricate shape and geometry. It serves as the foundation for the CFD analysis. Once the CAD model is complete, the next step is mesh generation. Meshing involves dividing the aircraft's surface and surrounding airspace into small cells. These cells form a grid that the CFD software uses to solve fluid flow equations. The quality of the mesh is critical for the accuracy of the simulation. A fine mesh with smaller cells provides more detailed results. However, it also requires more computational power. Engineers carefully balance accuracy and computational cost when generating the mesh. Section 4. Navigating the skies at supersonic speeds, simulating compressible flow. The F-35 is designed to fly at supersonic speeds. At such high velocities, the air's compressibility becomes significant. Compressible flow is characterized by changes in air density. These changes affect the aircraft's aerodynamic performance. To accurately simulate the F-35's flight, engineers use CFD software that accounts for compressible flow effects. This involves solving complex equations that govern the behavior of fluids at high speeds. Simulating compressible flow is computationally demanding. It requires powerful computers and specialized software. However, the insights gained from these simulations are invaluable for optimizing the aircraft's design. They help engineers understand and mitigate the challenges of supersonic flight. Section 5. Visualizing the invisible pressure, velocity, and drag force analysis. One of the key advantages of CFD is its ability to visualize airflow patterns. CFD simulations generate detailed maps of pressure, velocity, and other flow variables. These visualizations provide engineers with a deep understanding of how air interacts with the aircraft. For example, pressure maps reveal areas of high and low pressure on the aircraft's surface. High pressure areas indicate regions of high force. Low pressure areas can contribute to drag. Velocity vectors show the direction and magnitude of airflow. This information helps engineers identify areas of flow separation or turbulence. Drag force analysis is crucial for optimizing the aircraft's efficiency. CFD simulations can accurately predict the drag force acting on the aircraft. This allows engineers to make design changes that reduce drag and improve fuel efficiency. Section 6. CFD, a powerful tool for aviation innovation. CFD has revolutionized aircraft design and development. It allows engineers to virtually test and optimize aircraft designs before physical prototypes are built. This significantly reduces development time and costs. CFD also enables engineers to explore innovative designs and technologies that would be difficult or impossible to test physically. As computational power continues to increase, CFD simulations are becoming even more sophisticated. They can now model complex phenomena such as turbulence, aeroelasticity, and noise generation with remarkable accuracy. CFD is an indispensable tool for pushing the boundaries of aviation innovation. It plays a pivotal role in the development of faster, more efficient, and more sustainable aircraft. The F-35 Lightning II stands as a testament to the power of CFD in shaping the future of flight.